Well, good day, everybody. This is Chris back again with the Ancient Scholar, and we're going to continue our video series on the basics of mechanical ventilation, focusing on core concepts and universal terminology. So in the next video, I'm going to be relying fairly heavily on an article that was published in the journal Respiratory Care back in August of 2014. And I think it does a really good job of talking about basic universalizable language that can be used to understand or conceptualize mechanical ventilation. And the name of that article, if you want to reference it, is a Taxonomy for Mechanical Ventilation, 10 Fundamental Maxims. And what I'm going to do is I'm going to talk about each of the 10 fundamental maxims, because this is actually how we get into the nitty-gritty of defining mechanical ventilation and how we understand the concept of a mode of mechanical ventilation and in all of the various settings associated with that mode. And then what we can do is, once we understand the universal terminology, or a set of universal terms, because again, the language is not universal when it comes to individual companies, but starting at a foundation of language that we can all agree on, or that we will for this series of videos, we can then apply that to every individual manufacturer that may have specialized pet or trademark names for the modes, but at the end of the day, what is happening at a physiologic level is going to be related to what we're talking about here in the next couple of videos. And that is to say that a ventilator A may be doing the exact same thing physiologically as ventilator B, even though there are different naming schemes. And so to understand what's going on, we need to kind of understand the foundation. And the foundation really comes down to these 10 fundamental maxims of mechanical ventilation. So now that we understand what mechanical ventilation is at a basic level, what the indications are for mechanical ventilation, what some of the major complications are, and the 4 phases of a mechanically delivered breath, to include the control and limiting variables and the concepts of triggering and cycling. Let's expand that and map that onto these 10 maxims. And in this video, I'm going to talk about the first 5 of the 10 maxims. And they include the following. Maxim number 1. How do we define a breath? What is the universal definition of a breath? The universal definition of a breath is going to be one cycle of positive flow. So that is flow that is being delivered into, positively pushed into the respiratory system, i.e. inspiration, and negative flow, expiration, in terms of the flow time curve. So the flow time curve is a graphical representation of airflow going into the respiratory system, and we call that positive flow, all right? And going out of the respiratory system, being exhaled, is negative flow. Again, this is just the basic terminology, all right? That's what it means. And so when we graphically represent that, I have a little graph that I've drawn here. On the y-axis is flow, and the straight line in the middle would be 0. No flow at all. No flow in or out. So there's no flow going into or out of the respiratory system. And then if flow goes into the respiratory system, the waveform will go up. That's positive flow. And if air flows out of the respiratory system, it will go down. And so on the x-axis, you have time. So flow as a function of time is what we are looking at on the flow time curve. And this is actually a graphical representation of a breath that is used in this context to define a breath. And this is actually a graphic that some ventilators allow you to actually sense, detect, and look at sometimes in real time. All right, so we look at a breath. You have your expiratory pause. So that's at the end of exhalation. So you're exhaling. And at the very end of exhalation, when you quit, when air quits flowing, right before the onset of inspiration, you have your pause. So there's no airflow. And then what happens? The ventilator is triggered, inspiration starts, and air flows rapidly into the respiratory system. And so what happens is you have a rapid increase of positive flow into the inspiratory system. And if that flow is constant, right, if the ventilator is set to deliver a constant flow of maybe 60 liters per minute, right, then you'll have a straight line up here, all right, and this is what we call a square waveform. And sometimes flow can change. So the flow can decrease throughout the inspiratory cycle. And so instead of being square-shaped or plateau-shaped, it'll go up and then it will decrease down. And that is sometimes referred to as a descending ramp. Or sometimes it'll ramp up and then shoot down. That's called an ascending ramp. But there are many different ways that the flow rate can change during inspiration. But either way, when this is above the baseline, there is positive flow, and then that flow is constant here in this case, all right? And then at the end of inspiration, you may have something called an inspiratory pause, where you take a breath and you hold it. So you no longer have airflow, right? So there's no air flowing in to your lungs, but you're still in inspiration. You're just holding that air in. And so you may see the flow rate go back down to 0 because there's no airflow going into or out of the lungs, but the lungs are still full of air. And then you will cycle into expiration. And typically the expiratory graphical representation looks very different than inspiratory. Why? Because it is primarily a passive process, right? And so what you're going to see is you're going to see a line that is usually not going to be straight, right? Typically when you see a straight line, it's going to be the inspiratory flow, because the ventilator can basically instantly deliver a certain flow rate, whereas remember, even with mechanical ventilation, exhalation is primarily passive. And so what happens is you're not going to often have a straight line. You're going to have a curve as the airflow gradually increases over time. And then as you get to the end of the breath, the flow rate will gradually decrease till you get to the end of the expiratory cycle, where there is no more flow coming out of the patient. You go into your expiratory pause, and then it happens all over again. And from the expiratory pause to the expiratory pause, including the inspiratory flow time here and the expiratory flow time here, this is what we define as a breath, all right? And the amount of time it takes for the inspiratory and the expiratory is sometimes referred to as the total cycle time. All right, so that's the first maxim. The second maxim is a breath is considered assisted if the ventilator does some or all of the work of breathing. All right? So in order for a patient not to have an assisted breath, the patient has to do all of their own work of breathing. All right? So even if the ventilator is allowing the patient to spontaneously breathe, if the patient is receiving any support, right, any pressure support, positive pressure support, while they are spontaneously breathing, they are still receiving an assisted breath. All right? A ventilator assists using either pressure control or volume control, right? So we're talking about the control variables. A ventilator will use either pressure or volume to determine when cycling occurs, that is to transition from inspiration to expiration or inhalation to exhalation. And that is primarily based on the equation of motion for the respiratory system. What is the equation of motion for the respiratory system? I'm going to go over it real quick. And it is as followed. P applied, that is the applied pressure. So that is essentially the pressure the ventilator has to deliver to push air, deliver air into the respiratory system. All right, that applied pressure is equivalent to, in brackets here, parentheses here, R, which is airway resistance, multiplied by V dot, all right, which is flow, V dot, and this just relates to calculus, where one of the ways of writing a derivative is to put a dot on top of it, all right? It's a type of notation, right? That just means flow rate of a gas. So the airway resistance, think of airway resistance as the resistance the air encounters as it flows through the pipes of the lungs, right? So you've got little pipes, little airways, you've got your bronchi, you've got your bronchioles, and as air flows through, it can encounter resistance, right? And if you have mucus and the pipes constrict, you got what's called obstruction to airflow, okay? So you have to overcome resistance. Essentially, this part of the equation is airway resistance, overcoming the resistance, plus the elastance of the lungs, right? And elastance is essentially the lungs' desire, and I say that, and when I say desire, I don't mean that in any sort of conscious or anthropomorphic sense. I'm just saying that the lungs have a propensity to recoil, right? So they're kind of like a rubber band, and a rubber band is elastic because when you pull the rubber band and when you let go of the rubber band, it will recoil back to its original configuration. And so the propensity for lungs to recoil back is the elastance, right? And again, that recoil is primarily responsible for the passive exhalation that we see. Not only is it the lungs, but the chest wall, the relaxation of the muscles and the connective tissues of the chest wall, and even the abdomen can also play a part in the overall elastance of the lungs. Now, there is another concept called compliance, which is related to elastance, and compliance is the inverse. Mathematically, it's the inverse of elastance, and compliance is essentially the lungs resisting expansion, right? So if you resist expansion, you are less compliant or more elastic, right? The more elastic you are, the more likely or the more vigorously you are to go back or to recoil to your original state, right? So if you are poorly compliant, that means that the lungs do not inflate. It's harder to inflate them, and they are more elastic. So more elastance equals poor compliance, and poor compliance equals high elastance. They are reciprocal concepts to each other, all right? And so essentially it comes down to pushing air through the pipes, the resistance, plus the elastance of the lungs, plus whatever baseline pressure you're dealing with, right? Whatever baseline. If it's zero, if you're starting at atmospheric pressure and you're going to say that that's zero, then you'd start at zero. If your patient has some end expiratory pressure that is always in their respiratory system, we call this PEEP, positive end expiratory pressure, And so it's positive pressure that's always there. It doesn't matter if you're inhaling or exhaling, it's pressure that's always there. In a spontaneously breathing patient without an artificial airway, we would call this CPAP, continuous positive airway pressure. But in a mechanically ventilated patient with an artificial airway in, we would call that PEEP. So it's pressure that's always there. That's your starting pressure, right? So if it's 5 of PEEP, you would add that in as your baseline. So really all this is saying is the pressure that the ventilator needs to apply to cause flow is going to be essentially a product of the airway resistance in the pipes and the elastance of the lung tissue and the chest wall. And you have to overcome all that to drive air in to the respiratory system. Because remember, at the end of the day, you have to produce a driving pressure, right? So if you have a pipe and you want some fluid to flow through that pipe, of which air is a fluid, make sure, yeah, all right. What you need is you need to create a pressure gradient. You need to create a delta P, a change in pressure. This is often referred to as a driving pressure. All right, and so you're going to have, say, pressure 1 here on the left-hand side of the pipe and pressure 2 on the right-hand side of the pipe. And let's say that pressure 1 is 5 centimeters of water pressure, H2O, and pressure 2 is 30 centimeters of water pressure. All right, so the difference, the delta P from point 1 to point 2 is 25, right? That's the delta P. That's the pressure that is going to drive the flow of the fluid through that pipe. And in this case, right, what direction is the fluid going to flow, right? Well, it's going to flow, again, if you're talking about mechanical ventilation, you're pushing positive pressure, right? It's going to drive in this direction, right? Because you're applying this positive pressure here, and it is driving from the higher pressure to the lower pressure, right? In this direction, and the fluid will flow like that, all right? And then when you cycle into exhalation, right, this pressure needs to go down, and the flow needs to be driven in the other direction. And typically it's going to be a lot slower because the driving pressure is going to be a lot smaller. And again, a lot of that is going to come down to the elastance of the lungs and the chest wall. So that's just the basics of the equation of motion of the respiratory system. All right. Number 3, a ventilator assists using either, we talked about that. Number 4, breaths are classified by trigger and cycle. So when we classify mechanically delivered breaths, we categorize or classify those breaths by how they're triggered, right? And that is what we use to start the inspiration. Is it time? Is it pressure? Is it volume? And what are we using to cycle or stop? Again, is it typically going to be volume, pressure, something like that? All right? And these trigger and cycle events may be patient or machine initiated. If these events are entirely machine initiated, and that breath is machine initiated, this is often referred to as a mandatory breath. And that is a breath that is delivered. It is kind of like what the ventilator has to deliver at a minimum. That's a mandatory breath. And then breaths that are patient triggered and cycled tend to be what we call spontaneous breaths. And some mechanical ventilatory modalities allow for almost all spontaneous breathing. Some allow only mechanical or only mandatory, no spontaneous breaths, and then other modes allow for a mixture of mandatory and spontaneous breaths. All right? So hopefully things are starting to make a little more sense when we start thinking about how do I actually define what the ventilator's doing. When I select some mode and I put in some settings, how do they actually map onto the basic fundamentals of respiratory physiology? All right, those are the first 5 of the 10 maxims. I'm going to talk about the last 5, which are actually, from a practical standpoint, maybe a little more important when it comes to actually understanding a ventilator modes and settings. All right, everyone, I'll see you all in the next video.